The floor is yours.
I have to press a button, Rick? Or... No, we're good? Okay. Yep, hello. My name is Leo Parry. I'm a second-year PhD student here at the University of Nottingham. And today I would like to speak to you about the circular motion Unruh effect and a related effect, which we call the drifted Rindler Unruh effect. And I'm going to show you that there are some similarities between the two. Okay, so I want to begin with some motivation, why we're interested in the circular motion Unruh effect here. First of all, the traditional Unruh effect says that a linearly accelerated observer will experience the Minkowski vacuum as a thermal state with temperature which is proportional to its to the observer's proper acceleration. However, it's never been observed, and partly for two fundamental reasons. The first one is that it's a very small effect. So, for example, as we often say, to get a temperature increase of 1 Kelvin requires your system to be accelerating at 10 to the 20 meters per second squared. The second reason is that it requires a very large lab. So here I have a picture of the Stanford Linear Accelerator, which is around 3.2 kilometers long. So if we had a system that was accelerating at 10 to the 20 meters per second squared, it would travel the length of this accelerator in around 3 microseconds. So it's a small effect and it requires a large lab. So how do we overcome these obstacles? Well, the first one is to look at analog systems instead. So creating precise mathematical maps between difficult to observe, complicated, not well understood systems, and systems that we can implement in tabletop experiments, for example, in condensed matter systems. So here we have a picture of, we call it the big tank here in Nottingham. So this is our analog black hole. The other thing we can do is look at circular motion instead of linear acceleration. So like linear acceleration, this involves a constant acceleration. However, now we can contain the system in a finite size laboratory for an arbitrarily long length of time. Okay, and what I was interested in, or what I'm interested in, is different types of stationary motion in Minkowski spacetime. So, linear acceleration and circular motion are examples of stationary motion. A stationary world line is a world line whose geodesic interval depends only on the difference in proper time between points. And they're also the orbits of time-like killing vector fields. And in this talk, I'm going to focus on three of the types of stationary motion in Minkowski. So we have circular motion, drifted Rindler motion, and semi-cubical parabolic motion. So circular motion, it has, of course, this circular spatial projection. It is the orbit of a time-like translation and a spatial rotation. And this drifted Rindler motion, here's the spatial projection. It's a catenary, so it's a hyperbolic cosine. It is the orbit of a boost and a transverse spatial translation. So you're accelerating in one direction and simultaneously drifting with a constant speed in a transverse direction. Hence, drifted Rindler. And then the final type of motion I want to talk about is called semi-cubical parabolic motion. And in the literature, it's also been referred to as the parator and possibly something else, maybe cusped or something. So this is the spatial projection. You can see it's cusped. It's a semi-cubical parabola. And it is the orbit of a time-like translation and a null rotation. So what I want to talk to you about today is the geometric relationship between these three types of motion and how this translates to the response of an Unruh-DeWitt detector. So let's begin with the Unruh-DeWitt detector model. So we consider a point-like two-level system. So here it has energy levels 0 and 1, and the difference in energies between the two levels is E. We refer to it as the energy gap. And we use this system as a detector to probe a massless real scalar field phi. And we allow this detector to travel along a stationary world line, x of tau. Tau is the proper time. And we couple the detector to the field along this world line via this interaction Hamiltonian. So lambda is a small coupling constant. Chi is a switching function which tells you how to switch on and switch off your interaction. Mu is the monopole moment operator, which induces excitations and de-excitations in the detector. And phi of x of tau is the field evaluated along the detector's world line. In this presentation, we're going to think about chi as essentially being 1. So we're going to think about an interaction that's been on from the asymptotic past to the asymptotic future. And in this limit, we can define a transition rate. So the rate at which this detector makes transitions between its levels. Here you can see it's the Fourier transform of the Whiteman function, which is the 2-point vacuum correlation function. Okay, good. And okay, I should say we refer to this transition rate as the response function. So once we have the response function, we can extract this notion of a temperature using this detailed balance formula here. So we take the ratio of the de-excitations and the excitations, and then we can pull out a temperature from this formula. So for example, if you have inertial motion, this formula will give you t equals 0. If you have linear acceleration, this formula will give you t equals a over 2 pi. However, in general, for stationary motion, this temperature will depend on the energy gap. To truly determine if your state is thermal or not, you would have to have access to arbitrary energy scales and say, well, this detailed balance formula holds at each energy level. In any practical setting, you only have access to a finite window of energies. And we say, well, if the temperature doesn't vary too much on any interval, then we can say we have this notion of an effective temperature, which can induce heating in your system. Okay, good. Okay, so let's talk about circular motion and drifted Rindler motion. Let's talk about the geometry. So here on the left, we have circular motion. I've written the orbit here. So circular motion and drifted Rindler motion are both described by precisely 2 parameters. So in the case of circular motion, I've written it in terms of the tangential speeds of the circular motion, and r is the radius of motion. Gamma is the gamma factor, and the acceleration is gamma squared v squared over r. In the case of drifted Rindler motion, again, I've written it in terms of a speed parameter and a distance parameter. In this case, v is no longer the speed of the spatial projection of the world line. It's this constant drift speed. And r is the distance of closest approach to the origin in this coordinate system. And then we can use this speed to define a gamma factor. It's no longer the real gamma factor of the world line, but it's a useful parameter in this case. And the acceleration in this case is gamma squared over r. So already you can see there are some similarities between the two. So in a hand-wavy way, we can say there's something like a v goes to 1 over v duality on the level of these orbits. So if you send v to 1 over v, Yoma, close your eyes for this part. Gamma goes to minus I v gamma. So you can see, so if you take, for example, is this the thing? Yeah, okay. If you take the third component of the drifted Rindler orbit, let's look at the first one first. So you have this hyperbolic sign of gamma over r tau. So gamma becomes minus IV gamma, and this hyperbolic sign becomes a normal sign, and this gamma becomes a gamma v, something like that, okay? So this first component becomes this third component here, right? If you look at the second component, again, this hyperbolic cosine becomes the normal cosine, and this gamma becomes gamma v, something like that. And then finally, this gamma v tau becomes something like gamma tau, right? So there's something going on here. This clearly isn't a proof, but there's something going on here, okay? So what is going on? Well, in this paper here, it was shown that circular motion and drifted Rindler motion have the same limiting behavior in the ultra-relativistic limit with fixed proper acceleration. They both become semi-cubical parabolic motion. So this is this cusped motion I was talking about before. So how does that work? Well, for example, let's start with circular motion. So here it is. We want to take the v goes to one limit with a fixed. So this means that the radius is going to tend to infinity. So the first thing we do is translate by the radius. And then we perform this boost in the t and y. So the t is coming out of the board here. So we're doing a boost in t and y, t and y. And so this is going to stretch the world line because the r is increasing. So it's going to stretch in this plane, this direction. And it's also going to be squashed due to length contraction in this direction. And you're going to have some movement along the y prime axis. And then if we take then the v goes to one limit, then most of these, all of these sort of coils go out to infinity, and we're just left with what happens at the origin, and it turns into this cusped motion. So this is the semi-cubical parabola. And we can do the same starting from drifted Rindler motion. So again, here's the hyperbolic cosine. We're sending v to 1 with a fixed. R again goes to infinity. So we're going to translate by r first. And then again, do this boost in t and y. And again, we get this contraction in t and y. And then finally, if we take the v goes to one limit, again, if you zoom in here, you get this cusp. Okay, well, we can do one better than this. We can actually deform continuously circular motion into drifted Rindler motion. So if we start with circular motion and we make this transformation that I told you about in the previous two slides to cusped motion, to semi-cubical parabolic motion. And then what we're going to do is we're going to define new variables. So we're going to define this new capital V, which is 1 over small v. We're going to define this new acceleration, which is capital gamma squared over r. Capital gamma is 1 over the square root of 1 minus capital V squared. And then we're going to allow this small v to vary on the interval 1 to infinity. So we've gone through the v goes to 1 limit. So if v is now varying between 1 and infinity, this means that our new big V is between 0 and 1. So it's our new speed parameter. And so if you then do the inverse of the transformation that I told you about on the previous slide, you boost back away from the ultra-relativistic limit and you get drifted Rindler motion. So starting with circular motion, you send V to 1, and then you send V past 1, and you can get drifted Rindler motion like this. Okay, so something like circular motion with speed v and proper acceleration a is dual to drifted Rindler motion with speed 1 over v and proper acceleration, okay, a at minus a, it doesn't matter. So the question is, does this geometric duality translate to the experience of a detector? Yes and no is the answer. So in the ultra-relativistic limit, we found that the response functions for drifted Rindler and circular motion are precisely the response function for the semi-cubical parabola. Okay? And then, of course, the temperature is the same as well. In the large gap limit, we find that the drifted Rindler temperature is between the traditional Unruh temperature and pi over root 3 times the Unruh temperature, whereas circular motion is between pi over root 3 times the Unruh temperature and infinity. So, and this temperature here is, again, it's the temperature of the semicubical parabola, okay? Now, there's also the small gap, and it was found in this paper, which was done by lots of people here at Nottingham, that if you consider 2 + 1 dimensions, circular motion, and you take the small gap limit, we find that the temperature is linearly proportional to the gap as e goes to 0. So we find that the temperature is vanishing as e goes to 0. So we asked, well, is this also true with drifted Rindler motion? Does it also vanish in the e goes to 0 limit? And we found that, no, it doesn't. It's a constant in the e goes to 0 limit. Okay, then we asked, well, does it happen in 3 + 1 dimensions? No, it doesn't. So the temperature is, again, a constant in the small gap limit. So, well, drifted Rindler? No, it's also a constant in the e goes to 0 limit. So then we asked, well, when does the small gap temperature vanish? Okay, so here, this is the response function in 2 + 1 dimensions. You can write it like this. So here I've taken out a factor of s on the top and a factor of s on the bottom. Now we want to take the e goes to 0 limit of this expression here on the right. But in order to do that, we have to use the dominated convergence theorem, which, so we need to have this part of the, so this part is well behaved, right? This part is an integrable function. This part might not be well behaved, depending on the motion, okay? So for example, if this part dies as s goes to infinity, then we can take the e goes to 0 limit within the integral. However, if it doesn't, say for example, if it's a constant as s goes to infinity, we first need to subtract this large s behavior, and this is precisely what happens with this with the circular motion. So delta x, say, for example, if we say delta x squared is of order s to the alpha as s goes to infinity, where alpha is greater than 2, then the response, so then this part is of order e by the dominated convergence theorem, and we have something like a quarter plus a term of order e. And this gives a temperature which has a 0th order contribution, so it's a constant as e goes to 0. However, if delta x squared is of order s squared as s goes to infinity, then this part here is of order 1 as s goes to infinity. So say, for example, if delta x squared is something like s squared over a squared, where a is a constant as s goes to infinity, then we have to add and subtract this a from this term before we take the e goes to 0 limit within the integral. And this gives us another 0th order correction to the response function, which depends on the sign of the gap, like this. Okay? So we have this is a 0th order contribution, and this is going to be of order e. So if we plug this into the detail balance formula, we get that the temperature is proportional to the gap. Okay? So this only happens when delta x squared is of order s squared as s goes to infinity. So then the question is, well, which kind of motion has this property? So these are all the types of stationary motion in, well, I mean, we can forget about this one. This one doesn't exist in 2 + 1, the loxodrome. But let's think about these 5. We can ask, well, which of them has delta x squared is of order s squared as s goes to infinity? Well, the first one here is inertial motion, but inertial motion gives identically t is equal to 0, right? So we're not interested in that case. The only other one is circular motion. The other world lines, their delta x squared dies fast enough so that we can use the dominated convergence theorem. So this phenomenon is unique to circular motion in 2 + 1 dimensions. And yes, thank you for listening.